Okay, I guess I can start. Thank you very much, Olga, for the introduction. Hi, everyone. I'm excited to present our work, Effective Interplay between Sparsity and Quantization from Theory to Practice. This is a joint work across EPFL, Google DeepMind, and Korea University. We'll dive into the mathematical and empirical foundations of combining these two methods and how they interact in real-world models. As deep neural network models scale, their computational and memory demands grow exponentially. This plot shows the number of parameters in popular DNN models over the years. GPT-4 is estimated to have about 1.8 trillion parameters. This trend makes efficient inference and deployment more challenging, and compression is now not just an optimization, but it's a necessity. We focus on the two popular model compression techniques, sparsity and quantization. Sparsity works by pruning less important weights, and by this, the zero values can be compressed away to save memory. And also the ineffectual computations like multiplication and addition by zero can be eliminated. Quantization works by reducing the number of bits representing data. And this significantly shrinks memory requirements and speed up calculations. Essentially, quantization simplifies how data is stored and processed. But despite being widely used, these two techniques, how they interact when combined, remains an open question. Let's first look at the error introduced by sparsity alone. In this work, we focus on magnitude-based sparsity, and it removes insignificant weights based on their magnitudes, introducing a small but often tolerable error. For quantization, we focus on max scale quantization, where the quantization scale is chosen to be the largest element in a group of elements. Quantization introduces its own error by mapping values into coarser bins. This creates another source of distortion. So what happens when both are applied? They are often used together for maximum compression, and in this slide, we illustrate the error introduced by combining sparsity and quantization. The question is, can we assume that the total error is simply the sum of the individual errors? Previous work assumed that the total error is additive without extra interaction. That is, sparsity and quantization are orthogonal and can be stacked without compounding effects. But in our work, we show that this assumption does not hold. In fact, the combination leads to compounded errors, meaning their interaction can hurt model performance more than expected. So our first key contribution is providing a mathematical and empirical evidence that sparsity and quantization are non-orthogonal. This means that they interact, creating compounded errors that were previously underestimated. And this has critical implications for model accuracy and compression strategies. In addition to non-orthogonality, we also investigate the order of the operations. Here we have a small matrix. We first sparsify this matrix and zero out the smallest value, and then quantize it. If we calculate the mean square error, we obtain 0.1. However, reversing the order can significantly increase the error. Quantization might map these three values, as you see here, into the same bin and causing important weights to be removed incorrectly. So in this example, these three values are mapped to 1, and the sparsity operation will choose which one to zero out randomly. So we may end up removing the wrong element, meaning that the largest original value, and get much higher error. So in general, this may sound intuitive, but intuition can vary across researchers, and a formal proof provides an objective and universal explanation. So our second major contribution is the first mathematical proof that applying sparsity before quantization is the optimal order of operations. Here's a roadmap of the talk. We'll start with going into the details of these compression techniques, then walk through the theoretical findings, including the optimal order of compression and non-orthogonality of these compression methods, and then followed by experiments, and finally conclude with practical key takeaways. There are two types of sparsity schemes, unstructured and structured. And as the name suggests, in unstructured sparsity, there is no particular pattern when we sparsify the matrices. This can lead to more than 90% compression without losing accuracy. But it is not hardware friendly, and we need to keep track of which element we sparsify, and it changes across tensors, which would cause high metadata overhead. In structured sparsity, we follow a pattern to zero out elements, and as we are more restricted, we cannot compress as much. But it is hardware friendly because regular patterns are easy to compress and have low metadata overhead. And actually, there is already sparsity support in 800 GPUs from NVIDIA. And the particular scheme they support is 2 to 4 sparsity, or in general, they call it NM sparsity. And here in 2 to 4, we zero out 2 out of 4 consecutive elements, as you can see in the figure. So in our work, we investigate both cases. Quantization, on the other hand, comes in various flavors, and the traditional full precision format is FP32 with 8 bits of exponent, 1 bit of sign, and 23 bits of mantissa. There have been several proposals for a new numerical format for DNN training and inference, and every numerical format has a scaling factor, either implemented in software like the scaling factors in integer quantization, or in the hardware like exponent for floating point numbers. So we can divide all these formats into 3 categories with respect to the granularity and the level of these scaling factors. And I will provide one example in each category. For the element-wise scaling, the well-known format from Google Brain, bfloat16, it's just like FP32 has element-wise scaling factor. This means that each element has their own scaling factor. Scaling can also be blockwise, and this means that a block of elements share a scaling factor. And the blockwise scaling can also be divided into 2 categories, single level and 2-level blockwise scaling. Here you see HBFP8, or in more standardized formats, it's also the same as MXint8. And this is single level blockwise scaling, meaning that each element has their own mantissa and sign bit, and they share a group of elements share one scaling factor. In MXFP8, we have a narrower scaling factor for each element, and a block of these scaling elements share another scaling factor. If you're curious about how to support these blockwise scaled formats in tensor cores, you can check our latest ISCA paper. Here we explain how to bring microscaling formats into tensor cores. With this background in place, let's move to our main theoretical analysis, starting at the tensor level and moving toward dot product interactions. We begin by defining the error of transformation f on an input x. And this is the basis for analyzing how sparsity and quantization interact when applied in different orders. And this error is defined as the difference between the original tensor and f of x, which is the output of the transformation. So we define two transformations, f and g, to be orthogonal at the tensor level if any order of their composition does not introduce any additional error. So if the error of g of fx and f of gx are the same as the sum of their independent errors, then they are orthogonal. Now we prove that quantizing first and then sparsifying after can lead to extra, additional errors. And to prove that, it is enough to show that there exists at least one input x with a higher error of combination than the sum of the individual errors. And this happens because quantization may change the order of the tensor elements. We have x1 and x2 here, and the step here is the distance between two quantization bins. So the quantization operation will map the original elements into these bins here. Now, because of rounding, these two values can be mapped to the exact same bin as we saw in the beginning of the talk. And now when we sparsify, we may prune the originally larger element, leading to higher transformation error. We also derive a theoretical upper bound for this additional error. Here, the inequality you see is has our usual terms, the error of the combination, the sum of the individual errors, plus this additional error term, which gives our upper bound. The additional error depends on the step from this figure you see here, which was the distance between two consecutive quantization bins, and then the number of pruned elements. So this gives the number of pruned elements because NM is the sparsity scheme we mentioned before, and it can be generalized to unstructured sparsity. And N here is the quantization block size. It's the number of elements in a quantization block. I will not go into the details of this upper bound and the proof of it, but please check our paper for more details. Okay, when we come back to the order of the operations, applying sparsity first preserves the dominant values in a block, which means that the scale used in quantization stays the same because we are focusing on max scale quantization. What was that? It is the largest element in the quantization block is used as the scaling factor. So the error doesn't increase unexpectedly for a given tensor. Now, this is for a single tensor. What happens if we think about the DNN computations? Will this behavior hold true for the computations in DNNs? Now we established that at the tensor level, sparsifying first does not introduce any additional errors. Now let's zoom in further and look at what happens at the dot product level. After investigating the errors at the tensor level, we move on to the core operation of DNNs, which is the dot product operation. In our work, we focus on the general case where the weights are sparsified and both weights and activations are quantized. To continue with our proof, we need to define the error over the dot product operation when different transformations f and g are applied to the inputs, which is basically the difference between the original dot product and the dot product of the outputs of the transformations. Now, I show this slide, but it has a lot of symbols and math in it, so I will try to simplify what is happening here step by step and using words. Now, we say our theorem says that combining sparsity and quantization produces additional error in any order. So there exists an activation and weight vector such that Dot product error of compressed activations and weights is larger than the sum of the dot product error of sparsified weights and the dot product error of quantized weights and activations. So basically the error of the combination is larger than the sum of the individual errors, just like we did for tensor level, but this is now in the dot products. Moreover, we can set an upper bound for this error of the composition. And here, please note that I am using this specific order because we established that this is the optimal order at the tensor level. But we also prove this for both orders, also for dot products. But I am only showing the optimal order for tensor level here. Now we have the exact same terms for the upper bound, so the sum of the individual errors, plus some additional error coming from the interactions due to the dot product operation. Here we have epsilon I, which is the dot product between the error of quantized activations and the error of sparsified weights. And epsilon T, the dot product between quantized activation here and the correction vector. Correction vector is a term that carries the additional error from the tensor level to the dot product level. Now, I know it was a lot of math and notations, but at this point, I would say feel free to ask clarification questions if you have any. Okay, the remaining part will not have as much mathematics, so I continue and will leave the questions for later. We analyze these additional error terms to see how much they contribute to the total error. So we select random quantization blocks from the model and normalize their errors. Here the goal is to compare epsilon t and epsilon I we saw from the previous slides, and which one contributes most to the additional errors appearing in combining sparsity and quantization. We observe that epsilon t is generally higher than epsilon I, which makes sense because both dot product terms in epsilon I are the error values, and we have the quantized value of actual activations. We also observe the difference between these values is more dramatic for the suboptimal order, but I will not go into that. We also investigate how these errors propagate over the DNN layers. Now, let's look at a practical example using OPT 125 million. On the x-axis, we have the number of layers compressed starting from the first layer. On the y-axis, we have L2 error between the compressed network and the original one. We observe that the errors don't just stay isolated and they propagate through layers, becoming particularly severe in deeper network layers. This layer-wise propagation is much faster and more problematic when quantization precedes sparsity, which confirms our theoretical findings empirically. And even with the optimal order first sparsified and quantized, some cumulative errors still appear. And it is critical to acknowledge that optimal ordering mitigates but does not entirely eliminate compounded errors, which again confirms our theoretical finding about non-orthogonality. Let's move on to our experimental results to see how these theoretical insights play out in real models. We experiment across OPT, LLaMA, ViT, and ResNet. We compare several quantization formats, integer 8, HBFP, MXFP, as we show in the beginning, and the sparsity types like 50% unstructured and 2 to 4 structured sparsity. We apply sparse fine-tuning on a dense FP32 pre-trained model. And for the case of sparsified and quantized, we apply one-shot quantization on top of a sparse fine-tuned model. For the reverse order, we directly fine-tune the model in a quantized and sparsified manner. Finally, at each iteration, we quantize activations and weights and apply sparsity only to the weights. Here we show that the order matters. So in LLaMA 2 7 billion, applying sparsity first consistently gives lower perplexity values for both cases, for unstructured sparsity and structured sparsity, and for all the number formats you can see that the perplexity is consistently higher. And the suboptimal order can cause up to 8 additional perplexity points increase compared to the optimal order. To show the non-orthogonality empirically, we define orthogonality threshold, which is the sum of the perplexity of the dense and full precision model, shown as PPL here, and the individual sparsity and quantization errors in terms of perplexity. So if the compression methods are non-orthogonal, the perplexity of combination will exceed the orthogonality threshold due to the compounded error. And in most cases, even in the optimal order, the orthogonality threshold is exceeded in our experiments. And we observe up to 1.3 perplexity points additional error in LLaMA 2 7 billion. To wrap up, I'll summarize the key conclusions and implications of our work. We show that the order of applying sparsity and quantization matters. Applying quantization first can disrupt sparsity. So we provide the first mathematical proof that applying sparsity and quantization is the optimal order of operations. We also show that the errors don't just add, they interact. And these errors are input dependent, and so they are hard to predict. We offer both a theoretical framework and experimental results proving that sparsity and quantization are non-orthogonal. And this challenges prior assumptions and guides future compression design. So practitioners should be careful when compressing models, especially for safety critical applications. Thank you, and for more information, including code and the data, visit our project website, and I am happy to take any questions.